Download this code from codegive.com, link in the description below. Alec07 Interrupts, a comprehensive guide with code examples. Alec07 interrupts, also known as software interrupts or system calls, are a crucial mechanism for user mode programs to request services from the operating system kernel. They allow user programs to perform privileged operations, such as accessing hardware, managing memory, or interacting with the file system, without compromising system security and stability. This tutorial will cover the fundamental concepts of Alec07 interrupts, their purpose, usage, and how to implement them within a simplified environment. Disclaimer *: While the term Alec07 is often used to refer to a specific interrupt convention, this tutorial will focus on the general concept of software interrupts and how they function. The specific implementation details and interrupt numbers might vary significantly across different operating systems and architectures. This tutorial will use a hypothetical architecture and OS for illustrative purposes. Understanding the need for interrupts. Imagine a scenario where a user-level application wants to print a message to the console. Directly accessing the console's memory-mapped I/O addresses would be dangerous for several reasons. Security. A malicious program could overwrite crucial system data or take control of hardware. Resource management. Multiple programs might compete for the same resources, leading to conflicts and unpredictable behavior. Hardware abstraction. User programs would need to understand the specific details of each hardware device, making them difficult to port across different platforms. To address these issues, the operating system acts as an intermediary. User programs request services from the OS through a well-defined mechanism, interrupts. 2. What are software interrupts? A software interrupt is a special instruction that causes the CPU to immediately switch from user mode to kernel mode. This transition involves saving the current state of the user program, registers, instruction pointer, etc., and jumping to a predefined interrupt handler in the kernel. Think of it as a controlled exception. Instead of being triggered by an error, like division by 0, it's triggered intentionally by the user program to request a specific service. Key components *. 1. Interrupt instruction *. A special instruction, often named int, interrupt, syscall, or similar, that signals the CPU to trigger the interrupt. The instruction usually takes an argument, the interrupt number. 2. Interrupt number *. A unique identifier that specifies which service is being requested. For example, interrupt number 0x80 might be used for file I/O operations. 3. Interrupt vector table, IVT, a table in memory that maps interrupt numbers to the addresses of the corresponding interrupt handlers. The kernel initializes this table during system startup. 4. Interrupt handler *. A kernel mode function that processes the interrupt. It receives the interrupt number and any associated parameters from the user program. The handler performs the requested service and then returns control to the user program. 5. Context switch *. The process of saving the user program state, switching to kernel mode, and restoring the kernel state. This is handled by the hardware and the kernel's interrupt handling mechanism. 3. A hypothetical architecture and OS for illustration. To provide concrete examples, let's define a simplified architecture and operating system. Architecture 32-bit x86 inspired architecture with a flat memory model. Operating system Mini OS, a simple operating system with basic functionalities. Interrupt instruction int instruction, takes an 8-bit interrupt number as an operand. Interrupt vector table, IVT located at memory address 0x1000. Each entry in the IVT is a 4-byte address, 32-bit pointer, pointing to an interrupt handler. Therefore the interrupt handler address for interrupt n is found at address 0x1000 plus, n *4. Asterisk registers asterisk EAX, EBX, ECX, EDX, ESI, EDI, EBP, ESP, EIP. The return value from an interrupt handler is placed in the EAX register. 4. Example system calls in MiniOS. Let's define a few system calls for MiniOS, and assign interrupt numbers. Interrupt number, hex, system call name description parameters return value. Dash 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 dash. 0x01 sys underscore print prints a string to the console. EBX, pointer to the null terminated string 0 on success, -1 on error. 0x02 sys underscore exit terminates the program. EBX, exit code. Never returns. 0x03 sys underscore read reads from stin. EBX, pointer to buffer, ECX, size of buffer number of bytes read or -1 on error. 0x04 sys underscore open opens a file. EBX, pointer to file name, string, ECX, flags, example read/write, file descriptor or -1 on error. 0x05 sys underscore close closes a file descriptor. EBX, file descriptor 0 on success, -1 on error. V implementing the interrupt handler, kernel side. This is a simplified example of how an interrupt handler might be implemented in the MiniOS kernel. The actual implementation is highly dependent on the kernel's structure and programming language. This assumes the kernel is written in C and assembly language. Explanation of the kernel code asterisk. 1 interrupt underscore handler, this is the main interrupt handler function. It receives the interrupt number and the register's values. 2 switch statement, it uses a switch statement to determine which system call was requested based on the interrupt number. 3 system call implementations, each case in the switch statement calls a corresponding function, example kprint, kexit, to handle the specific system call. These functions perform the privileged operations. 4 isr underscore stub, this assembly code saves all general purpose registers to the stack, saves the stack pointer and instruction pointer, EIP, to allow returning, and saves the interrupt number, then it calls the actual interrupt handler, the C code. Finally it restores the registers before returning to the user space via iret. 5 set underscore interrupt underscore handler, this function writes the address of isr underscore stub to the correct entry in the interrupt vector table. 6 initialize underscore interrupts, sets up the IVT to point to the defined handlers. 6. Using the interrupts, user side. This section shows how a user program would use the defined system calls. This code also assumes it's compiled for the MiniOS target. Explanation of the user code asterisk. 1 syscall function asterisk, this is an inline assembly function that makes the system call. It loads the interrupt number and arguments into the appropriate registers, EAX, EBX, ECX, EDX, and then executes the int instruction. 2 calling system calls asterisk, the main function demonstrates how to call the defined system calls, sys underscore print, sys underscore exit, sys underscore read, sys underscore open, sys underscore close. 3 passing arguments asterisk, arguments are passed to the system call through registers. 4 receiving return value asterisk, the return value from the system call is placed in the EAX register. The syscall function retrieves this value and returns it to the caller. 7. Building and running the example, simplified. Since this is a hypothetical system, we can't compile and run it directly on a standard OS. We need a simulated environment. Here's a basic outline. 1. Assemble and compile *. Use an assembler, like NASM, an AC compiler, like GCC, to compile the assembly and C code into object files. You'll need to configure the compiler to target the hypothetical architecture, 32-bit x86 inspired. You might need cross-compilation tools if your development environment is different from the target architecture. 2. Link *. Use a linker to combine the object files into a single executable. You need to specify the entry point, example main in the kernel, and the memory layout, where the kernel and user code will be loaded. 3. Simulator/emulator * use a CPU simulator or emulator to execute the generated binary. A simple simulator would need to load the kernel and user code into memory. Initialize the CPU registers and the IVT. Start execution at the kernel's entry point. Emulate the int instruction and the context switch. Handle the interrupt handlers. Provide a simulated console for output. 4. Debugging * use a debugger that can work with the simulator to step through the code, inspect registers, and examine memory. 8. Important considerations and limitations. Security * proper validation of parameters passed from user mode to kernel mode is crucial to prevent vulnerabilities. The kernel must carefully check the validity of pointers, sizes, and other arguments before using them. Stack management * switching between user and kernel modes requires careful management of the stack. The kernel must have its own stack to prevent user programs from overwriting kernel data. Concurrency * if the operating system supports multiple processes or threads, the interrupt handler must be reentrant and thread safe. Synchronization mechanisms, example locks, may be needed to protect shared data. Real-time systems * in real-time systems, interrupt handlers must execute quickly and predictably to meet deadlines. Interrupt handlers should minimize the amount of work they do and delegate more complex tasks to background threads. Architecture-specific details * interrupt handling is highly architecture-specific. The exact mechanisms for saving and restoring context, switching modes, and accessing the IVT vary significantly between different CPU architectures. Simplification * this example is a huge simplification. A real operating system would involve a much more complex implementation, including memory management, process management, device drivers, and a sophisticated interrupt handling system. The missing pieces are stack setup for both user and kernel, memory allocation for the user process, and a complete IRET implementation. 9. Beyond the basics. This tutorial provides a foundation for understanding Alec07 interrupts. To further your knowledge, you can explore the following topics. Protected mode and ring levels * understand how the CPU's protection mechanisms are used to enforce privilege separation between user and kernel modes. Interrupt controllers, PIC/APICs learn how hardware interrupts are handled by interrupt controllers and how they are routed to the CPU. Exception handling * explore how the operating system handles exceptions, example division by zero, page faults, and how they relate to interrupts. System call interfaces * study the system call interfaces of different operating systems, example Linux, Windows, and how they are implemented. Kernel development * dive into kernel development and learn how to write device drivers, memory managers, and other kernel components that rely on interrupts. Conclusion. Alec07 interrupts are a fundamental mechanism for allowing user mode programs to request services from the operating system kernel in a safe and controlled manner. By understanding the concepts presented in this tutorial, you will gain a better appreciation for how operating systems work and how they protect the system from malicious or buggy user programs. Remember that the specifics vary between different systems, but the general principle remains the same.